Hi, this is Mr. Woodbury from College of the Sequoias. This video is for my Math 21 class. We're in section 12.2 covering the chi-square independence test. All the data in this video can be found in the Woodbury Math 21 StatCrunch group under section 12.2. This test is the chi-square test for independence, and it's used to determine whether there's an association between a row variable and a column variable in a contingency table constructed from sample data. The null hypothesis is that the variables are not associated. In other words, they are independent. The alternative hypothesis is that the variables are associated or dependent. Here, we will not be using any symbols in our null and alternative hypothesis. I'll show you what that looks like in a couple of the examples. For an example of a type of claim that would lead to this test, we would see something like test the claim that a person's burger preference is independent of the person's gender. One categorical variable, burger preference, being compared to another categorical variable, a person's gender. And we want to see if there's a relation between these two variables. Now, it doesn't mean that one completely determines the other. What we're trying to see is whether one increases the chances or decreases the chances of certain categories in the other variable. To identify this test, first, the claim will involve one categorical variable being independent of another categorical variable. Second, you have to have a contingency table. The observed frequencies are the sample frequencies found in the cells inside the table, and we label those as O sub I. The expected frequencies are what we would expect to see if the two variables are indeed independent of each other, and we call that E sub I. StatCrunch behind the scenes will be calculating E sub I using this formula. It multiplies the total of the row that it's in by the total of the column that it's in, and then divides by the sample size. This comes from independent table probabilities way back in chapter 5. Let's talk about the differences for the test. The null hypothesis will always be of this form. Variable 1 is independent of variable 2. So again, the null hypothesis is always that they're independent or unrelated. The alternate hypothesis will always be that variable 1 is dependent on variable 2. That means that they are related. One depends on the other. No differences in step 2. For step 3, we call this the test for independence. In step 4, these are the steps that you need to follow to compute the test statistic and p-value in StatCrunch. Begin with stat, tables, contingency with summary. Put the row labels in the first column and make the header for the first column the row variable. Enter the column labels as headers in the next columns. Enter the summary data from the contingency table in the correct rows under those column labels. Basically, we're trying to reproduce the contingency table inside StatCrunch. Next, select stat, tables, contingency, and with summary. Select the column variables. The column variables are the ones that have the observed frequencies or observed counts underneath them. Then select the column containing the row variable. Select expected count under display because we need that to check the conditions. Chi-square test will already be highlighted. Click compute, and you'll have your test statistic and p-value. The formula for the test statistic is shown here. This is the same as in the goodness of fit test. We subtract each expected frequency from the observed frequency and square the difference. We divide that square by the expected frequency, and then we total this for each cell. The distribution we're using is the chi-square distribution, and again, this is the Greek letter chi. Let's talk about the conditions for this test. To perform a test for independence, the following two conditions must be met. First, each expected frequency has to be at least 1. So if we have an expected frequency below 1, we cannot do this test. At that point, we can combine two columns or two rows in such a way that the expected frequencies will be greater than or equal to 1. Also, no more than 20% of all expected frequencies can be less than 5. When we're computing the test statistic and p-value, StatCrunch will give us those expected frequencies, and that's where we'll check the conditions. If all of the expected frequencies are at least 5, then we're good to go. If you have any below 5, then you have to make sure that none of them are below 1, and the number that are below 5 can be no more than 20% of all the expected frequencies. The data can be found in the StatCrunch group Woodbury Math 21, and the name of that file is section 12.2. Here's the first example. A random sample of 483 workers were asked how they saved their things, in piles, in files, or some combination of both. Here are the results broken down by gender. At the 0.05 level of significance, test the claim that the technique used is independent of gender. So we know we're working with a hypothesis test. We're asked to test a claim, there's a level of significance. And here's the first key, that the technique is independent of gender. One categorical variable is independent of another. Also, we have a contingency table here. Across the top, piles, files, and both, these are the technique that's used. Down the side, we have the genders, male and female, and I'm going to write the header gender above that. And what I'm going to try to do is retype this table in StatCrunch exactly how as I see it. There we can check the conditions and also compute the test statistic. Let's start to write this up first. The null hypothesis is that the technique used is independent of gender. That means that we're assuming that technique and gender are unrelated. One does not impact the other. The alternate hypothesis is that technique is dependent on gender. This means that there is a relationship. Now, the order here is important. The technique that you use will not impact your gender, but we're checking to see if your gender might impact the technique that you use. And so we say that technique then would be dependent on gender, rather than gender being dependent on technique. The level of significance was 0.05. The test is the test for independence. Now's the time that we'll do our calculations inside StatCrunch and check the conditions. Let's go to StatCrunch. For this example, I have the data in the first 4 columns. The first column contains the row labels under gender, and the next 3 columns, piles, files, and both, contain the data. To begin, we press on Stat, Tables, Contingency with Summary. For the columns, we select piles, files, and both. For row labels, that was under gender. And we need to ask for the expected count under display because that's how we'll check our conditions. Press Compute, and we begin by looking at the expected counts, which are in the parentheses inside the tables. Notice that none of these values are below 5, so all the conditions are satisfied. Our test statistic for chi-square is 10.10 with a p-value of 0.0064. Okay, all the conditions were satisfied. Chi-square was equal to 10.10. The p-value was 0.0064. That is less than the level of significance, so we're going to reject the null hypothesis. That means that there is sufficient evidence to conclude that H1 is true. In other words, technique is dependent on gender. In other words, there is a relationship between the technique that's used and a person's gender. Now for example 2. A random sample of 425 Americans were asked whether they had health insurance. Here are the results broken down by race. At the 0.01 level of significance, test the claim that race is independent of health insurance status. So here we're testing a claim that race, one categorical variable, is independent of health insurance status, another categorical variable. Also, we have a contingency table. We see 4 races listed at the top, as well as 2 insurance statuses listed on the left-hand side. Above insurance and no insurance, I'm going to write status. And I'm going to try to reproduce this table inside StatCrunch. Let's begin by starting to write up the test. The null hypothesis is that insurance status is independent of race. The alternate hypothesis is that it's dependent on race. The null hypothesis, we're assuming that these two categorical variables are independent, meaning unrelated. And in the alternate hypothesis, we're trying to prove that insurance status is dependent on race. Now, again, the order is important here. We would not say that race is dependent on insurance status because your insurance status will not change your race, but the other may be true. So we want to write them in this order. Sometimes the two variables could affect each other, then it doesn't matter what order you write them in. The level of significance was alpha equals 0.01, and the test is the test for independence. Okay, let's go to StatCrunch, enter the data, compute our test statistic and p-value while at the same time checking the conditions. Here in StatCrunch, I have the data in columns 6 through 10. The row variables are in column 6 under status, and the expected frequencies are in columns 7 through 10. To do the calculations, press Stat, Tables, Contingency with Summary. The columns are Asian, Black, Hispanic, White, non-Hispanic. The row labels are under Status, and again, under Display, we need to ask for the expected count. Press Compute. Notice that none of the expected frequencies inside the table, inside parentheses, are less than 5, so the conditions are satisfied. The test statistic chi-square is 11.03, the p-value 0.0116. The test statistic was chi-square equals 11.03, the p-value was equal to 0.0116. That is not less than the level of significance, so that means we failed to reject HO. In other words, we cannot say that HO is false, and that means that there is not enough evidence to prove that H1 is true. In other words, insurance status is dependent on race. So we were not able to prove that that is true. Notice the low level of significance here. If this problem had been at the 0.05 level, our decision and conclusion would have changed. We would have rejected the null hypothesis, saying that it's false, and we would have concluded that there was enough evidence to support that insurance status was indeed dependent on race and that the two categorical variables are related.